Hello and welcome to the Math 200 lecture series for Cañada College. We are using PowerPoint presentations created from Mario Triola's textbook, Essentials of Statistics, 5th edition. My name is Ray Lapuz. We are in Chapter 10. Let's take a look at the review and preview in 10-1. In Chapter 9, we took a look at methods for making inferences from two samples. More specifically, in 9-4, we looked at two dependent samples where we paired up the values. So in this chapter, we're going to consider another set of paired values, but this time we're not going to look at it as paired of the same types of values like before and after grades or before and after measurements of the body like blood pressure or heart rate. We're going to look at two different types of quantitative variables that would pertain to a particular data set. So our preview would be looking at correlations and associations between two variables. We're going to focus on linear correlations. Now we have to understand that there are other nonlinear correlations that exist, but in this particular chapter we are focused on linear correlations. Section 10-2, Correlation. The main idea here is to define a correlation coefficient which will give us a number that measures how well a paired sample data fit together in a straight line pattern. Finding this number R, the correlation coefficient, is kind of daunting if you were to try to do it by hand. So we will focus on using our calculators to find this value. Again, we are only considering linear relationships, and so when we find these values, we're looking at it from a linear point of view. We will also develop a hypothesis testing for correlation. So let's take a look at the basics of correlation. So correlation exists between two variables when the values of one are somehow associated or related with the values of the other. A linear correlation exists between two variables when there is correlation and the plotted points of paired data result in a pattern that can somehow follow a straight line. So it's important for us to take a look at data from a graphical point of view, and for that we will be looking at scatterplots. So let's take a look at some scatterplots with corresponding correlation coefficient values. So in our first example we have a positive correlation of 0.851. So if you look at the data, it looks like it follows a straight line that goes upward if you look at it from left to right. A negative correlation would be when the set of dots, or these data points, seem to be moving downward from left to right. So in this case we have a negative correlation of negative 0.965. When your data seems to not follow a line, then your correlation coefficient would be 0 or close to 0, and then we would say that we don't have correlation in this case. And remember that we are only measuring the linear correlation or the linear relationship. So we have an R value again that's fairly close to 0 at negative 0.087. However, we can see that there is another pattern that is emerging here that is not linear. So again, we won't be looking at these things, but they do exist. So what are the requirements for a linear correlation? First of all, we want to make sure that our sample data is simple and random, and they come in an ordered pair value. And we can look at it as an XY value, where X is the first variable and Y is the second variable. We also want to be able to look at a scatter plot to confirm the points are approximately a straight line pattern. And then that's when we will find our correlation. If there are outliers, that might be some errors. Say you're typing in the data and then you mistype the number, then they can be removed, and removing this would help us find a stronger R value. The formula for correlation is, again, quite difficult, and they involve a lot of summation. That's the sigma symbol. And so we're going to take a look at it, but we will not be using that formula. I just wanted to show you guys how it might look like and how people used to do it by hand back in the old days before we had technology. So here is the linear correlation coefficient formula, and it measures the strength and direction, whether it's positive or negative, of a linear relationship between paired data. Alright, we're not really going to be using this, so let's move on. The R value that we get is something that we can assess and be able to tell whether there is a strong linear correlation or not. And in general, we use the Pearson's correlation table, that's table A6, to give us some idea whether we have a correlation or no correlation between the values. As we're using the calculator, our calculator will also be able to give us the p-values. And so what we can do is we can use the same p-value results and decisions whether to reject or fail to reject the null hypothesis. So when we go further into our hypothesis testing in this chapter, we'll see how the p-value plays in. So some words of caution. The methods that we're applying here are only for linear correlations. So if you see a slightly different pattern, like maybe an exponential curve pattern or parabolic pattern that we saw earlier, then there's a different sort of test for that we're not going to cover. Here are some properties for the linear correlation coefficient R. If you've noticed in our first few examples that R is never less than -1 or never larger than +1. Our R values are always between -1 and +1. We get -1 if we have a perfect correlation that is going down, decreasing, so it's a negative value, or we get +1 if we get a perfect positive correlation. And then in the middle of that is 0, and when you're close to 0, we have no correlation. We also have these other properties. If all values of one or both variables are converted to a different scale, say you're moving from inches to centimeters, then the value of R does not change. Also, the value of R is not affected by your choice of x and y. So if we type in the x's and the y's and we find a correlation coefficient, and we switch the x's and the y's, we will still get the same correlation coefficient. Another reiteration of the fact that this is a linear relationship. R measures the strength of a linear relationship, not any other sort of curve that might happen. And then R is also sensitive to outliers, which can dramatically affect the value. Let's take a look at an example. Here's a small list of shoe print lengths and heights of males. And let's see how we can examine this data set. Just a quick check, we want to make sure that the sample is simple and random, and it's a paired data set, so it has x values and y values. We tend to put the x values in the horizontal direction and the y values in the vertical direction. And it's not exactly a straight line, but it looks like it might be following a line, so we can say that this might have some good correlation. So here are a handful of technologies that can be used. We'll focus on the TI-8384 calculators. And so let's take a closer look at how to do that. In our calculator, first thing we want to do is we want to enter our data into the lists. And in general, we want to use L1 and L2. So if we clear that out and enter the data, that's a good place to start. We could take a quick look at the graph by hitting the second function or the second button and then the y equals to, and then that will bring us to the stat plot. If your plots are all off, then that's fine. If any of these plots are on, if more than one plot is on, then maybe you want to turn all the plots off and start over. But in general, we want to go to plot 1, turn that on, and then we're going to select the scatterplot type of graph, and that's going to require us to input the x list and the y list, so we just put L1 and L2. Most of this is already there, and then the mark we want to use is the square, so that gives us a larger viewing of each of those dots. And if we hit zoom and then we look for zoom stat, which is the number 9, we can see our data set. Now to find the R value, we want to go to stat, and then the right arrow brings us to test, and then we're going to hit up or down to get to the lin-reg t-test. So we get to the lin-reg t-test, and we're going to set it up where the x list and y list are L1 and L2. The frequency is going to be 1. Now this is going to be always our alternative hypothesis for a test, for a hypothesis test. And so we want to just make sure that we keep it at a not equal to 0 symbol. The regression equation is y1. We can store our regression equation there, and then we can ask it to calculate. And when we calculate, we get a set of values here from a t to the p, df, a, b, s, r squared, and r. So the r is, for right now, our main focus, and it's the same r value. That's 0.591. Now this y1 regression equation will store our equation into the y1 function. And if you run this test and then try to see the plot again, this time we would have the equation of the line. And so that y1 gives us the equation of the line after we do this test. So technology is recommended. Just make sure you use your calculators for this. So the question here is that, is there correlation? Is there linear correlation? So our R value of 0.591 is going to be our key. So if we want to try to interpret this meaning, what we want to do is we want to compare this value to some sort of critical value. And that critical value is something that we can find in table A6. If we're using the computer we can also find the p-value. So what we can do is that our p-value can just be compared to our significance level, which is, if it's not given, it's 0.05. Those values that we would find in table A6 would be coming from that table A6, and in this particular example we have 5 pairs of data, so that table is going to lead us to a 0.878 critical value. And so that critical value would be a good marker to decide whether we have correlation or no correlation. Numbers close to 1 would give us stronger correlations, and numbers close to 0 would give us no correlations. And that critical value from table A6 would be our splitting value, our critical value that would split the correlation and no correlation. In the output, we also get an R squared, and R squared is the proportion of variation in y that's explained by the linear relationship that's given between x and y. So in our example, we had, again, r is equal to 0.591 and r squared is 0.349. So about 34.9% of the variation is explained by the linear relationship between them. So that's how we can interpret r squared. Let's take a quick look at some common errors. The biggest error that we can make in correlation and studying correlation is that if there is a correlation between two variables, people tend to imply a causation, that one variable is causing the other to happen. And this is not a good conclusion, because in studying correlation, all we are doing is finding out if there's a relationship between two variables. And we are not looking if one variable is causing another. We are only looking for association or relationships. Another error that happens is an average. If you take averages of things, then that tends to make your correlation coefficient bigger than what it might seem. And linearity, again, this is a test for linear correlation. There might be some other relationship that is happening between the variables that's not linear. Alright, now that we got through the basics, let's go through the hypothesis test. And in hypothesis testing, we're really asking the question if there is a linear correlation between two variables. So our notation, we're going to establish a notation here. Our n is the number of pairs, our r is a correlation for the sample. Now, since this is a statistic for a sample, we are going to need a parameter for the population, and that parameter is given by rho. This P looking symbol here is actually a Greek letter rho that is the same as an R in Greek, and so this is our population parameter for the correlation coefficient. So we have some requirements, again simple and random. It looks like the visual gives us some sort of idea that the scatter plot is showing a straight line pattern and outliers are taken out. So in a hypothesis test, we start off with the null and alternative hypothesis. And the null hypothesis is always going to be rho is equal to 0. And when we say that rho is equal to 0, that's your correlation coefficient. It's far away from 1 and -1 where you have strong correlation. And so you're at 0, which is to say that there is no linear correlation. Our alternative hypothesis is the claim that we're making. We're asking if there's a linear correlation. So we can assume that there is a we can test that there's a linear correlation, and that would be our claim. Some important values are the test statistic R, and the test statistic, this is actually going to end up being a t-test, so we can look at the t and also the p-values. So we saw that if R is close to 1, then it surpasses the critical value, and then this symbol that we're seeing here, the absolute value, just allows us to take a look at the positive side as well as the negative side, and these values are close to 1. So if the R values are less than the critical value, that means we're closer to 0, and when we're closer to 0, we say that there is no correlation. This is really a formal hypothesis test, so once you have the value for R, you can find our test statistic T. And if you remember, we are testing this using the linear regression t-test, so this is really a t-test. And we're going to use a t-distribution. Instead of using the t-distribution, we're going to stick with the p-value analysis. So we'll just be looking at the p-values and comparing it. So let's do the formal hypothesis test here. So we're going to test the claim that there's correlation, and we set up our null and alternative hypothesis. Now remember, our test statistic is 0.591. So 0.591 is, in our linreg t-test, 0.591 is that value all the way at the bottom, so you have to scroll down to actually get it. We saw that our critical value is 0.878, positive and negative 0.878, and we saw that this number, 0.591, our R value, is closer to 0 than it is closer to 1 compared to this 0.878 number. So right here we can already stop and say there is no linear correlation. But we're going to push on and take a look at the p-values here. And so doing it by hand, you would first have to find the t-value, that's a t-test statistic, and then from there find the p-value. Well, you don't have to go through this formula, or you don't have to go through table A3, because you can find that in your calculator. And in our calculator, the t-value and the p-value are the first two values that they give in this linear regression t-test. So we got a t-value, a test statistic of 1.269, and a p-value of 0.237. So that's our test statistic and our p-value that we want to be able to report. Now, since the p-value is greater than the significance level, we're going to fail to reject the null hypothesis. And so we're going to come to our conclusion, and our conclusion is that there is not enough evidence to support the claim of a linear correlation between the shoe print and the heights. There's some information about one-tail tests that we're not really going to cover too much, but it's an interesting idea if we're testing for positive or negative correlation. Okay, so this is an interesting slide to look at, but we're not really going to focus on this. So that brings us to the end of section 10-2.